Thank you very much, Jörg, for the nice introduction, and I would like to thank also Ulrike for giving me the opportunity to talk in this very nice kickoff meeting of TACO. So today I'm going to show you some of a flavor of how we try to understand heterogeneous catalysts and the challenges to model these materials by using a theoretical approach. Actually, the goal of our research is in the energy field, so we try to understand processes that take CO2, ideally, that would be the ideal scheme, and use intermittent energy sources from renewable energies and transfer it to, or transform it via catalysis to this kind of compounds that are highly energy density materials. The systems we are actually interested in are heterogeneous catalysts, and here I show an example of the materials we are mostly interested in. So these are generally solid particles supported on a high surface area support. And many of these materials are already known to catalyze some of these all related transformations. And as you can see, well, there is a broad rich chemistry involving transformations between CO2, CO, to methanol, to methane, and so on, and that would depend on the metal you have, the oxide you have, and so on. The questions we ask ourselves as a theoretical group, because we are using theory, is to first try to start by the simplest model we can think of, which is a catalyst that is not immobile, where the reactants come, evolve, and produce given products. And these are the questions we are mostly interested in when we go to more complex and technical systems: the active site, the mechanisms, where the reaction takes place, or how the catalysts change their operation conditions, and how we can capture this by using theoretical approach. And a great deal of our work is also collaborating with experimentalists in order to benchmark our theoretical methods and try to get the limitations we have in order to move forward in our research. So that would be the general scheme. A heterogeneous catalyst is a highly complex material, and there are several processes occurring at different scales. So from the atomic level, here you can have also a great deal of complexity. And there are things happening on the nanoscale, mesoscale, and so on. Okay. And depending on the scale we are looking at, then we use different techniques. So generally, our main focus is on DFT calculations and also ab initio molecular dynamics. And I will show some examples of this during my talk today. And we are then also interested in some cases, try to predict or construct kinetic models to understand catalysis at the global scale, to get more coverage and rates. And you could eventually go until the continuum level where you had heat and mass transfer effects. But that would be the main focus of our talk today. So here I summarize the processes that we have been working on and the different reactions we have investigated. And today I will focus on methanol synthesis and hydrocarbon conversion. Generally, this methanol synthesis is catalyzed by copper systems on different oxide supports. And then the second part of my talk, I will discuss a bit about alloy particles supported on gallium on a silica surface that has some gallium single site on it. Coming to the first topic, that's CO2 hydrogenation. This reaction produces methanol, and that's the interested product that we want to obtain. And that's what was proposed by Ola in this methanol economy project. However, you have a selectivity problem in here because methanol is not the only product you can have, but you can also convert CO2 with hydrogen and form CO and water, and that would be your undesired product. And that depends basically, your product outcome depends basically on the support you have. If you support copper, which is the active catalyst generally for this reaction, and if you support it on this kind of oxides, then you form mostly CO, whereas when you support it on other type of supports, like zirconia, for instance, you form selectively methanol. And that would be what I will first look at it. So what is the support effect, and what's the difference between copper supported on silica, that is a rather inert support, versus copper support in zirconia. And you can already see by this diagram that copper on silica is rather unselective, so you form basically 50% of methanol and 50% of CO, whereas zirconia is not really, or is much more selective towards methanol. So this is this red graph here, and much less selective towards CO. So in order to try to understand this, we constructed a model of different model systems. So this is a model catalyst. So we didn't explore in depth the configuration space like in the first talk, but we were interested more into the intrinsic catalytic activity of these different materials. So CO2, for instance, if you try to absorb it on copper, it doesn't really can absorb. It's basically physisorb. On the oxide, the absorption energy is stronger, and when you put CO2 on the interface, you see this is very strong interaction energy. And if you look at the charge of the CO2, you see that CO2 has less positive charge than in here, where it's basically the gas phase molecule, and that charge actually has come from the oxide support interface. So you can actually bend the CO2 by absorbing it at this interface. And then looking back into the fundamentals, that's the CO2 molecular orbital diagram of the CO2 molecule and what happens when you bend the molecule. So you start by this configuration where the molecule is linear, and when you bend it, you can see that these two orbitals that they generate here, they split into two, the in-plane one here and the out-of-plane here. And that one now is more prone to receive electronic density. And we think that is what happens and what we saw before on the interface, that the interface transfers negative charge to the CO2 molecule. That allows it to bend. And basically, since this molecular orbital is more accessible, then you have more availability to transfer electron density to this orbital here, and that stabilizes the system a lot. And you can imagine, if you look at the molecular orbital diagram of formate, what happens when you have formate? Well, this stabilizes even more. So then, looking into the catalysis of how this system could work, we look into the free energy calculation of this reaction, so checking which could be the intermediates, and having CO2 and formate as key species. Hydrogen can actually absorb on the particle and be transferred to CO2, form formate, then acetal, and eventually methoxy. And these are two species that were actually detected by NMR by our experimental collaborators, and this is Christophe Copperet and co-workers. So I just briefly talk a bit about what's the effect of the support. However, there is also a possibility of an effect of a particle size. So how the particle size affects the catalysis you have in there. And this is former work by the group of Hansen, where they propose that actually small clusters are more active in CO2 hydrogenation than big clusters. So the idea here would be to eventually go to very small systems, and that would be a single atom catalyst of this kind that you can have in many different catalytic systems, and that's a review by Pedro Ramirez from last year. That's not a new idea, because anyway you found them on many systems, but still the idea is to try to find a system that's able to graph and stabilize this copper on molybdenum carbide, and then check if it performs CO2 hydrogenation to methanol. And the group of Christoph Müller actually managed to do that. So copper and few atom cluster, I would say. So the cluster size ranges from 1 to 4. And if you support it on a molybdenum carbide, then you have this kind of system that is very, very active in CO2 hydrogenation in comparison to copper on silica or the industrial copper zinc oxide support. And if you then try to assign what is the site responsible for catalysis, and these are hydrogen programmed desorption experiments, you see actually that on the most active system you have an additional peak here at higher temperatures in comparison to the reference catalyst with pure copper. And not only that, but if you contact CO to this system, you see this additional signal here that is actually a signature of copper delta plus site. So that would be the two main known things experimentally from this material. So then we came up with trying to model or understand what is the active site of the material. And what we did was the following. So we constructed kind of a calibration curve in which you plot the oxidation state, again, reference compounds. So these are known compounds, surface of copper, copper 2O, and copper oxygen, where you know which is the oxidation state. We calculated the charge. You draw a line. And then we constructed different models of how this cluster of copper can be on the surface that have basically different oxygen content. And then if you then interpolate in here, you can see that there are some models of this kind that have a copper somewhat delta plus site. And then if you calculate the CO absorption of this, it's rather strong, and you see a signal that's also in the range of the experimental signal where you have a signature of copper delta plus. And in addition, I should say also that the hydrogen absorption is much stronger on this interface than it is on the system where there is no oxygen around. So then we tested we computed the catalysis of this system. And that gives rise to some chemistry that is more molecular-like and not that surface-like in a way. So CO2 can react with hydrogen in this kind of transition state, forming formate. And you see that CO2 is mostly molecular here, and hydrogen comes, forms formate, and eventually you have another hydrogen molecule that comes, reacts here, and forms this oxymethylene, and eventually this leads to methanol. And these are the two key transition states you have for that transformation. That's actually quite particular of this kind of system where you have a copper atom on a support and not a particle or not an oxide. So here, a bit more of discussion of this. If you check at the charge of this system and compare it against somewhat classical copper 111, you see that the charge is like that. So you have some difference in polarity between these two hydrogens. So this one is delta plus, this one is delta minus, and this is the same for this transition state and for that other transition state. And this is rather different to what you have on the case of a copper 111 surface, where you don't have much difference in polarity between the activation of the two activated hydrogen molecules. And in addition, for this system, there is only another particularity, and this is that there is one reactant that's mostly adsorbed. In this case, would be hydrogen. In this case, it would be this formate. And there is another one that mostly comes from the gas phase. So you also have this kind of irreducible path in which instead of having things coming to the surface and react, you have one thing adsorbed, and then there is another one coming from the gas phase and reacting. So that kind of system gives you access to do somewhat a bit of different chemistry that can be interesting in catalysis. Okay, the system is not actually very selective towards methanol. It's highly active, but not selective. So that should mean that the routes towards CO, they shouldn't be difficult, at least. And actually, if you absorb CO2 on this interface and you cleave it, you see that the barriers are very low. Actually, you can form CO easily, and that competes with pure methanol hydrogenation. Of course, in order to know which is the main composition or which is the ratio, you would need to then construct a kinetic model. I don't know if we will do, but in any case, at least on a quantitative level, we can first know the nature of the site and then rationalize somewhat catalytic activity that is experimentally found. So I've shown you some examples of this, and now on my second part of my talk, I would like to show you some examples of this kind of system in which I will show you not only static, but also ab initio molecular dynamic calculation, in which dynamics of this kind of particles is important, because under these conditions, the hash conditions you need in order to promote this transformation, these particles are mostly liquid-like rather than having a particular configuration. Okay, so that's some generalities of the reaction. So basically, it's rather energy demanding, and that's the problem, because then you have some paths that you don't want, because that's a path you want. You take hydrogen out of propane, and you form propene. Okay, However, at these harsh temperatures, you can also cleave bonds, carbon-carbon bonds, and also at the same time remove hydrogen, forming coke that it's then deposited into your catalyst and then is basically dead. So that's the experimental system we try to understand from a molecular perspective. I think I will skip this part of describing this system. The idea here was first go to the static level, what is the effect, and try to evaluate what is the effect of introducing gallium into the system in comparison to pure platinum that is also known to be active for this reaction, although much less selective, so it forms much more coke. And we tested the most stable phase of platinum to gallium. And one interesting aspect is that when you put gallium into the platinum, the system becomes much more amorphous-like. Okay, so that's we run into. I mean, we did extensive exploration of many bulk facets, then surface terminations, and so on. And we found that the flat surface is like that, flat like with some gallium in it, is a bit more amorphous than the regular platinum 111. And there is this also other structure which has kind of a step platinum, that is platinum enriched, that is also quite stable. If you then try to compare what happens when you absorb propane in these two systems, so for the case of the chemisorb system, that's just phase absorption. For the case of chemisorb system, you see that the CH elongates a bit and interacts mostly with platinum on the platinum to gallium. And here, this is the analogous with the platinum surface. You see that the absorption energy is a bit stronger in here than here. And on this step side, that's even stronger, as it would be also the case for a pure platinum step system. Then we look into the reactivity of that, first just by using this static approach. So the reaction we are interested in is you take propane, then once a bond is activated, you have propyl, and then there is another activation forming propene. And we compare the three systems, and you can see that the introduction of gallium increases the energy barriers. These are the two paths on this flat surface in comparison to the platinum, pure platinum. However, when you have this step surface with gallium, you have somewhat smaller energy barrier here and similar energy barrier in here. However, this is just the static approach. And the system, I should say that also not only has platinum, but also has some gallium on it, on silica. Okay, so there are different phases that contribute to catalysis. So on a separate study, we just check on the activity of this guy here, gallium. And based on a model I constructed some time ago, we tested the activity of different sites. But basically, the main idea of this slide is that gallium is much less, significantly less active than the platinum alloy system. Okay, so but that gives you an idea of how different models on these amorphous systems, how is the energy profiles can really change a bit when you change the site morphology from one to another. So that's just different kind of models of the same kind of electronic structure, but different degrees in strain in here, and you see how much the catalysis can be there. Okay, so that was concerning the static approach, but what happens when you consider dynamics of this? Well, first we run optimization and then ab initio molecular dynamics on pure platinum on silica and of this alloy system on silica. And you see that no matter what we did, we also did extensive search, but more than the most stable structure, what interests us is the changes between pure platinum and a platinum to gallium system. You see that when you have a pure platinum, you have somewhat more spheric situation, whereas when you have platinum gallium, you have it more spread on the surface. And here you see the superimposed image of the molecular dynamics. So here, this is, I don't know if you see, but this represents the movement of platinum during dynamics, so it doesn't move much. It moves, but not much. However, you see here how the particle changes very much under high temperatures when you have some gallium on it. Okay, that's just the intrinsic nature of the dynamics of that, but what happens when you have the reaction? Well, in order to see the reaction to take place, you really need to give it some asteroids, okay? Otherwise, you will never see anything happening if you place propane and you run up initial molecular dynamics, because just the particle and propane would move, but nothing would happen, so there would be no reaction in there. So one possible approach is to use metadynamics, in which you try to evaluate the free energy surface as a function of some coordinates. In our case, coordinates would be the reactants we're interested in, so propane that reacts on platinum, and possible changes on the CH bond coordination number in the middle of propane, and this other CH coordination number in the other end. So you need to activate two of these bonds to actually form propene. And in this approach, what you do is you basically give energy. So you put hills here, represented by this Gaussian function. And with this, you aid the system to move up in your free energy profile. Then you move to another well, and so on. And by knowing or having an idea of how much of this, you have an idea of how much is the energy cost you pay in order to go from one well to another. So in other words, you reconstruct the free energy surface. Okay? And this gives you a bit of more flexibility. Of course, we want this to happen, nothing else, but we don't know, or we don't have the system information beforehand of whether this reaction will take place first or this other reaction will take place. So then what we did is to compare both systems. So you have the platinum, the silica support, and the propane. And then you run the simulation, or you do the simulation. This takes a lot of time, and you have to play a lot with the parameters of the hills you put, how much energy, and so on. And you see that the platinum moves, but not really a lot in comparison to the CH. And then you have first cleavage of the CH molecule, which is the first step of the reaction. And after a while, you will have the other step that cleaves the second CH bond. Yeah, that comes here, and then you have propene, that is your final product. And then this eventually would join and then form H2, but I skipped this. So now the idea is to compare this system with the alloy system, where you have platinum to gallium. You see the particle that is somewhat more amorphous, and then actually the reaction happens before, and happens on this more of step side. There is this platinum atom that is a bit pull up on the system, and eventually this also happens, the second activation happens on this kind of system too. And if you compare if you run the movies like fast forward, you see that here the particle moves, but not really a lot, or as much in comparison to here, where you have a big movement of the particle. So we think that the reason behind this higher activity of this platinum alloy system is because of this high mobility of gallium that introduces the possibility to form more of a step platinum atoms that are a bit more active and react with propane to form propene. Sorry. And you see also that when you look at the energy diagram that you get. So when you compare the two systems, you see that the platinum to gallium is much more active than the platinum system. So we think that is this insaturation that leads and high mobility of the system. When you have gallium, that increases the activity of those. So we also check into the coke. I will summarize this a lot, but basically we did also some dynamic simulation of this. But here I just show a bit of the static results. You see that when you have, at least the trend is that when you have the reaction of cracking on platinum sites with gallium nearby, it seems to be much higher in energy. We ran also the molecular dynamic simulations for the particle I showed before, and we also see that the reaction takes longer when you have the alloy than when you have the pure platinum system. Okay, so with that, I conclude. Well, these are the constructions that I discussed along my talk, and I would like to thank the people involved in the work. So my group in Barcelona, some former collaborators and present PhD student at TTH, my Indian connection, CS Praveen, the funding, and all of you for your kind attention.
Thank you, Aleix. Yes, questions? So before the propane dehydrogenation, you had images of two clusters, platinum and platinum gallium. And one of the clusters was clearly the platinum gallium, but the other one had green atoms as well. I was a little bit confused. Yeah, I think, yeah, that's it. What are the green atoms there?
Yeah, because it's the gallium on the surface.
Okay, I see.
Yeah, I mean, I didn't explain a lot, but the catalyst has platinum. I mean, because it's the way you synthesize the catalyst experimentally. They graph gallium on silica, they have gallium. Then they deposit platinum. They cook it up, and they form this platinum to gallium particles, but you still have some gallium in your support that stays there, okay? But just this pure platinum. It's also, I didn't explain this in detail, but it's also true that platinum, where you start growing, we also check a bit of where platinum wants to sit at the beginning, and it interacts more with platinum. The platinum you put interacts more with the gallium you have already in there. That's why you have some green atoms also nearby the platinum.
So I was wondering about your about the dehydrogenation reaction. The movies that you showed show that the two hydrogens, they are removed separately from the propane. Wouldn't you expect that it should be easier if it happens in a concerted way? And would your collective variables be able to produce that reaction?
In principle, they should be able to cover this path if it's more preferred, because you just tell somehow the system to activate these bonds, and not how this happens. So it seems that when you have this kind of systems, it goes in a stepwise way rather than in a concerted way. And then, yeah, we didn't model that, but eventually you will need the two hydrogens to couple and remove H2. But in principle, the variables cover that. It's also true that you would need also to run many simulations, and maybe in some of these, you would be able to find a configuration where you also find this path you mentioned. But in principle, the system should, or if it happens this way, it's possibly the most likely way, I would say. That's
yeah, thank you, Aleix. Wonderful. So with this platinum gallium, I understand that the nice aspect of the system is that at the operation or the reaction temperature, it's actually liquid, right? So,
yeah.
so my question is then,
not liquid,
you presented first more static concepts with the DFT calculations and this MD calculations, right? How much, if you have a liquid system, is it very different, or can you still learn something from the static calculations, or it's maybe more a philosophical question when you go from a heterogeneous catalyst that you think of maybe fluid but still solid to something that's really liquid and changes all the time?
Yeah, maybe more than liquid, one could say it's more mobile, and one is more mobile than the other. Of course, that's what our calculations try to predict. And the second.
Yeah, if there's a real difference between something that's really liquid at the operating temperature, but also maybe more static, still fluxional, but more static.
Well, the way we understand, we think that at least for these particle sizes that are also the ones that resemble most experimentally, we see that this higher mobility isolates, in a way, it's also, there's another aspect here, so platinum steps maybe form more easily on this kind of systems, or steps, one could say, more saturated. And the other aspect is that propane doesn't like gallium at all. So propane does want to interact with platinum rather than with gallium, And because of, from one side you have this higher mobility in here than in there, and from the other side you have propane that wants to react only with platinum, not with gallium. These two things we think that are behind to have higher activity on this system than on the other one.
I would like to return to the methanol synthesis. There you had the copper atoms residing on top of the surface. And it seems that the high reactivity comes from that position.
Which one? The copper on zirconia, you mean?
This one, yeah.
This one.
On molybdenum carbide.
Yeah.
So the high reactivity seems to come from the presence of the copper atom on top of the support. And I mean, both here, where it serves to create a favorable transition state, and also on one of the next slides where you had the CO binding very strongly to that copper. And my question is doesn't that reflect that the copper is in a high energy state, and as time goes by, it would be sort of absorbed in the support in some position? I mean, it could not happen in this system, but if you had steps or other kinds of defects, then it would not remain as this protruding atom, and perhaps its magic would disappear.
That could be. It's also true that they check by TM before and after catalysis, and they didn't see a bit of I mean, not a big difference when you have a starting system and after operating for a while. Well, here on this case, I would say it's a bit different than the other, because this case you have CO2 that is a bit more, I mean, in this case of configuration, not on this transition state. CO2 and a hydrogen react kind of simultaneously, whereas on the other you have CO2 interacting directly with copper. It's also true that, yeah, I mean, when you have this in this case, when you have this system, yeah, you can also argue, I mean, that there is some kind of defect here, but that doesn't depend much on the kind of configuration you have in there for the copper, I would say, for this system. The other one, yes, I mean, it's true that it's very unsaturated, so it's possible that after a while this moves and goes to a more stable position. That I cannot deny that. So.